Okay, hey, welcome back. So this time we're going to get formulas for arc length and surface of revolution. Arc length is a little bit more important to me. We'll use it later on in Calc 3. Surface of revolution, in my experience, not so much, but your experience may differ. Anyways, let's get the formula for arc length. First off, we need the mean value theorem. Mean value theorem from Calc 1. And basically, you need a function that's continuous and differentiable on an interval. And if that's true, you could do this substitution. So if you have f of b minus f of a all over b minus a, which is basically some sort of slope-looking thing, you could turn around and substitute the derivative evaluated at some point in the interval. We'll need that. We also need the distance formula, so I hope you remember that. Distance formula, d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay. And we're just going to derive the formula then. Okay. So the derivation, I guess we'll call it. So visually, the scenario, we have some curve in the plane. And then what we're going to do is basically just section it up and measure the little sections with a ruler, right? So we'll start at A, go to B, begin at this point, we'll call x0, comma y sub 0, and then just go to this next point here, depending on some change in x distance, and then use a ruler to measure that straight line distance. And you keep on doing that, blah, blah. And here we'll kind of dot, dot, dot. Then you have sort of a general interval, and then you keep doing that all the way to the end, and we're going to call the end x sub n comma y sub n. These two in the middle will be x sub n minus 1 comma y sub n minus 1 for this guy, and then this point right here will be I, not n, I apologize. X sub I minus 1, y sub I minus 1, and then this is x sub I comma y sub I. What we're going to try to do is create a Riemann sum that we could take the limit of, and then we'll get an integral out of it. Okay, so that's the picture. Literally, we can then transcribe that into a formula so that the approximation of the arc length, which we're going to use the letter S for some reason, is just going to be the sum of all these little line segments. So going to the distance formula and using the generic points x sub I, y sub I, x sub I minus 1, y sub I minus 1, we get the sum of all of these distances as x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. And we're going to go from I equals 1 to n. Okay? So that'll give you the sum of the distances of all those little blue line segments. Let's go ahead and rewrite x sub I minus x sub I minus 1 as change in x, and this as change in y, just for notational issues. So we'll have the square root of change in x squared plus change in y squared. We can make it look like a Riemann sum. We need like some function of x here, f of x sub I times change in x, right? So we can do that by factoring out a change in x. And we get the sum of the square root of 1 plus change in y over change in x squared times change in x squared. And then the square root of a product is the product of the square roots. So you get the square root of 1 plus change in y all over change in x squared times change in x. And then this thing right here, because of the mean value theorem and because of the properties of the function, the assumed properties, so over here, note we consider a function that's continuously differentiable. And if you have that, you can use the mean value theorem on any of these subintervals to find a c value such that we can replace this or do a substitution and rewrite the expression as 1 plus f of c sub I for some c sub I in the interval from x sub I minus 1 to x sub I, and rewrite our Riemann's, now it's a Riemann sum, right, from I equals 1 to n. It's kind of a Riemann sum. It's not quite because we don't have an x sub I in there, But we're going to be able to take the limit of this thing. So taking the limit, we have the exact value of the arc length will be the sum of these little distance increments. As the intervals go to 0, that c sub I kind of gets smushed, and we could rewrite it as the integral from a to b of the square root of 1 plus f prime of x squared. This thing should be squared, sorry, dx. And that will be the integral for arc length that we need to do the problems in this section. The real hard part for these problems is just the kind of algebra. Let's take a look at example 1 before we get too deep. And we can actually look at the WebAssign problem that you'll be facing. Basically, they want you to figure out the distance. So this is problem 1 from WebAssign. Figure out the distance between these 2 points using the distance formula and then using integration. Okay. So a from the distance formula, d is the square root of x2 minus x1 squared plus y2 minus y1 squared. And what is that? Square root of 9 plus 4, so square root 13. For our integral, we need this f prime of thingamajig. But if you're talking about a line, y equals mx plus b, the derivative is just the m, right? So all you need really is the slope to put that integral together. So note here the slope is y2 minus y1, so 3 minus 1 all over x2 minus x1. So that's just 2 all over 3. So we can dump that and then into our formula for arc length. So s equals the integral of the square root of 1 plus, it'll be the slope squared, so that's 4/9 dx. And the x values are going from 1 to 4, so those will be the limits on our integral. And so we have the integral from 1 to 4 of the square root of 9/9 plus 4/9 is 13/9 dx. You could factor that out of the integral. It'll be square root of 13 over 3 when you simplify. And then you just have the integral from 1 to 4 of dx. So that'll be square root 13 over 3 times x evaluated from 1 to 4. And of course, that's just going to be root 13 because you'll have, okay, so root 13 over 3 times 4 minus 1. Root 13 over 3 times 3 will just give you the root 13, and sure enough, okay, you get the same answer. Right, so there's that idea. They go through it in a general way in the book, so you can kind of see the mechanics of it all. Let's look at example 2, and we're going to make this one the video quiz for this section. Video quiz, right? Video quiz, video quiz, video quiz. You'll kind of appreciate that the algebra involved in the integral is kind of weird. Anyways, x cubed over 6 plus 1/2 x to the negative 2 on the interval from 1/2 to 2. So y prime, let's get that out of the way. 3x squared over 6 is x squared over 2. Then minus x to the negative 1 over 2. So what power rule negative 2. What the heck is, it's to the negative first power. Sorry about that. So negative 1 all over 2x squared. It's like I sort of already know the answer, so I'm like trying to think it through, but at the same time I know what it is. It's confusing. Okay, so the first one is 3x squared over 6. The second one plus 1/2. Bring down the negative 1 and then x to the negative 2, right? So you get x squared over 2 minus 1 all over 2x squared. Okay, okay, that's that thing. You may want to go ahead and FOIL it, because you're going to have to get the derivative squared for our formula. So just remember what the formula is. It's the derivative squared. So sometimes they'll want you to do that. Just get it out of the way. So anyways, to multiply that out, you can bring out the 1/2, and then you have x squared minus x to the negative 2 squared. Then, product to power rule, if you have a, b to the second power, that's a squared times b squared. So here it's 1/2 squared is 1/4. And then you have to FOIL the x squared minus x to the negative 2. Right? So you can end up with 1/4 times x to the 4th minus x to the negative 2 times x to the 2 is just 1. X to the 0 is 1. So you get minus 1 is minus 2, and then plus x to the negative 4. Okay, so my arc length is going to be the integral from 1/2 to 2 of the square root of 1 plus this 1/4 times x to the 4th minus 2 plus x to the negative 4th dx. Okay, so the tricky part here is rewriting this so it's a perfect square, and then you can take the square root of it. Okay, so what I'm going to do is first factor out a 1/4. Okay, so you get 4 plus x to the 4th minus 2 plus x to the negative 4th. You can factor out the 1/4 of the radical and then the integral. So you get a 1/2 integral square root, combining like terms. 4 minus 2 is 2. So you get x to the 4th plus 2 plus x to the negative 4th, which is quadratic in form. Okay, it's a perfect square trinomial, so to speak. So you can factor that into a product of two of the same binomial. So in particular, it's x squared plus x to the negative 2 squared. If you don't believe me, you could FOIL that out. You'll get x to the 4th plus 1 plus x to the negative 4th. And of course, that's where you started. Right? So it works. Okay, so anyways, then you can take the square root of that thing, and you just get the x squared plus x to the negative 2. And now you're kind of home free because you just do power rules. So you have x cubed over 3 plus x to the negative 1 over negative 1. Clean it up a little bit. And then do your sub in the limits into the antiderivative. So 8/3 minus 1/2 minus 1 over 24 minus 2, apparently. So that'll be 1/2 times, you need a common denominator, 24. So 8 times 24, so 64 all over 24 minus 12 all over 24 minus 1 over 24 plus 48 all over 24. So 64 plus 48, 8, 9, 10, 11, 12, carry the 1, 1, 1, 2. Minus 12 is 100, minus 1 is 99. So I'll end up with 99 all over 48. You can divide top and bottom by 3, so you get 33 all over 16, I believe. Let's see if they got, yeah, okay. Great. You could do other orientations for arc length. So in this case, we did kind of the x-axis version, the Riemann man running in this direction, collecting up these little length increments. But you can reorient everything if you have a curve that maybe is a non-function in the x orientation and put it like this. Then your Riemann man is just going up the flagpole, and your integral will be the square root of 1 plus g prime of y squared dy. Okay, so let's look at this example 3. You're kind of forced to do it in this way because the derivative wouldn't be defined. So anyways, let's take a look. Y minus 1 cubed equals x squared on 0 to 8. I'm going to solve for x, so I get x equals y minus 1 to the 3/2, just take the square root of both sides. And then I'm going to integrate, instead of going from 0 to 8, then I have to go from 1 to 5, and you can see the coordinates in the picture. on the right here, bottom right. So the integral now would go from 1 to 5, the square root of 1 plus the derivative of x squared. So x prime is 3/2 times y minus 1 to the 1/2. Squaring that would be 9/4 times y minus 1. Okay. By the way, that previous problem was a video quiz, again, in case I didn't mention that. So here we have the integral of 1 plus 9/4 y minus 9/4. Simplify that. So we get the integral of the square root of 9/4 y minus 5/4 dy. I'm going to do a u sub, or 9/4 y minus 5/4. My du would be 9/4 dy. Dy would be 4/9 du. So I'm also going to change the limits here. So u of 1 would be 9/4 minus 5/4, which is 4/4, which is 1. U of 8 would be really? U of 8 is that? Did I write that right? It's yeah. 8 to 72/4 minus 5/4. Seems like it worked out real nice last. Oh, it's to 5. Sorry. So yeah, so that would be 45/4 minus 5/4 is 40/4, which is 10. Okay, so my new integral is u to the 1/2 times 4/9. You could plot the 4/9 du. The new limits 1 to 10. So I get 4/9 times u to the 3/2 times 2/3, 1 to 10. This should be 8/27 times 10 to the 3/2 minus 1 to the 3/2, just 1. Go through there and see your answer is the same. Yeah. Okay. Okay. So example 4. You have to use some trig identities to pull that one off. So you got the y is ln of cosine of x. They tell you they want the arc length on the interval from 0 to pi over 4. So get the derivative. It's 1 over cosine x times negative sine x. Sine over cosine is tangent, so you get negative tan x. Dump it into your arc length formula. So the integral from 0 to pi over 4 of the square root of 1 plus negative tan squared x is tan squared x dx. And then we could use our Pythagorean identities to simplify that, reminding ourselves sine x squared plus cosine x squared is 1. Dividing everything by cosine, you get tan squared plus 1 equals secant squared. So I could replace 1 plus tan squared with secant squared. You got the square root of secant squared x dx. And just take the square root of secant squared, that's just secant x dx. And then you may have to look up that one, but it's the ln of the absolute value of secant x plus tan x from 0 to the pi over 4. Then substitute in the limits. So you get the ln of the square root of 2 plus 1 minus the ln of the absolute value of 1 plus 0. And then you can pump that into your calculator, get your answer. Okay. They use, so one application here is finding the length of a cable. So let's look at number 8 from the book, or from WebAssign. They model the equation of the cable using this thing, x over 20 plus e to the negative x over 20. The telephone poles are 40 meters apart, so you can kind of put them into the xy plane and locate this guy at 20, 0, locate this guy at negative 20, 0. And then they have a cable hanging between the two, and it's modeled by that function y. Okay, they want to know the length of that cable. So I'm going to use the arc length formula. First, I'm going to recall that cosh of x is equal to e to the x plus e to the negative x over 2. Okay, so cosh of x over 20, guess what, is e to the x over 20 plus e to the negative x over 20 over 2. So I could replace this stuff in the original equation, e to the x over 20 plus e to the negative x over 20, with 2 cosh of x over 20. Okay? And that's what I'm going to do. So my y is going to be 20 cosh of x over 20. All right. So my arc length formula S is the integral of the square root of, I need the derivative, so y prime is going to be 20 sinh of x over 20, and then the chain rule 1 over 20. So that's equal to sinh of x over 20 for my derivative. So I have 1 plus that thing squared, so sinh squared of x over 20. Then this thing, believe it or not, we can simplify it in the same way we kind of simplified back here. I don't think the book does that, but you can do that. And it's identity that's kind of similar to the Pythagorean identities is that cosh squared x minus sinh squared x is equal to 1. So you could replace 1 plus sinh squared with cosh squared. And that will work out real nice for us. I'm also only going to integrate from 0 to 20. So I'll get half the arc length from here to here. And then I'm just going to multiply by 2. So I put the 2 out in front because it's symmetric about the origin. OK, so I have 2 times the integral of the square root, and this will become cosh squared of x over 20 dx. And of course, that will be 2 integral of just cosh of x over 20 dx. You could do a u sub. You'll end up with a factor of 20. So you'd end up with 40. The integral of cosh is sinh. And that would be sinh of u, but then back subbing, you'd get x over 20. And then evaluate from 0 to 20. So you'd end up with 40 times sinh of 1 minus sinh of 0. And then remind yourself what sinh is. So sinh of x is equal to e to the x minus e to the negative x over 2. So sinh of 1 is going to be e to the 1 minus e to the negative 1 over 2. Sinh of 0, though, will be 0. Because it'd be e to the 0 minus e to the 0, which is 1 minus 1. Which is 0. So we'd end up with 40 times e minus 1 over e all over 2. In other words, 20 times e minus 1 over e. And then they want 3 decimals. You could just go to Wolfram and figure that out. Okay, so 47.008, which is what you see my answer is here. The next section is on arc length. So you need surface area, sorry. So you need arc length in order to do surface area problems because of the formula for surface area. So we'll begin with basically just the same picture as before. We have some sort of region that we're rotating about the, in this case, x-axis. And we'll consider one little piece of it here, but weirdly enough, we're not going to use quite a rectangle anymore. We'll use kind of a trapezoid figure. Then we'll rotate that, and we want to find the surface area of this object, which is basically a frustrum of a cone, like a chopped off piece of the cone. Okay. I kind of think of it as like a strip of paper, but you know, whatever gets the job done, right? Okay, there are 2 basic dimensions we need. We need this length here, which will basically, you always think of that as your radius, and then this length here, which we get from arc length, the L value. So the surface area of that frustum, you could call it change in S sub I, would be 2 pi RL. And in terms of f of x's and x's, that will be 2 pi. The r value would be f of x sub I. And then the L value comes from the arc length formula, so that would be 1 plus f prime of the c sub I squared, change in x. Okay? So the formula in general then, if they're not being mean, would be surface area equals 2 pi integral of some radius function, I'll just call r of x, times the square root of 1 plus this f prime of x dx, whatever that function is that describes the curve in space, okay, from A to B. And of course you can orient it with regards to y as well. Let's just look at whatever heck kind of problem they have for us. Well, actually, let's go to the WebAssign problems. Kind of try these guys. All right, so let's try this one, number 10. Set up and evaluate the definite integral for the curve. They give you the formula for the curve y equals 1/3 x cubed. Looks like I'm going, from the picture, I'm just going from 0 to 3, so that's not a mystery at all. At 3, it would be 27 over 3, so that would be 9. 1, 2, 3. So it's like this trumpet object. Okay, you need the two elements again. You need like this radius function, which is basically just going to be the height of this particular rectangle. So r of x, we could just say is 1/3 x cubed. And then the L of x, which is basically that square root thing, is going to come from this function that describes the curve. So I need the derivative, y prime will be 3 times 1/3 x squared, so it just ended up being x squared. So L of x will be the square root of 1 plus x to the 4th. Okay? So your integral for the surface area would be 2 pi integral from 0 to 3 apparently of 1/3 x cubed times the square root of 1 plus x to the 4th dx. You can just do a u sub on that. So u is 1 plus x to the 4th du 4x cubed dx. So dx is du all over 4x cubed. And then we got 2 pi integral 1/3 x cubed times u to the 1/2 now times dx, which is now du all over 4x cubed. We have 4 times 3 is, so 1/12, 2 over 12 is 1 over 6. Then we have a pi. The x cubes cancel, integral u to the 1/2 du. So we get 1/6 pi u now to the 3/2 times 2/3, evaluated from 0 to 3. Eventually, I have to back sub first before I can say that. So it'll be 1/3, so 1/9 pi times 1 plus x to the 4th to the 3/2, evaluated from 0 to 3. So that would be 1/9 pi times 3 times 3 is 9, is 20, 81, so 82 to the 3/2 minus 1 to the 3/2, just 1, like that. So let's see if we got it. 0 to 3, this thing is something weird. 1/3 x cubed times square root 1 plus x to the 4th. And then we're getting this thing. We want 2 decimals, so I'm going to go over to Wolfram. Um, 23.532. 3.532. Of course. Oh, I just typed it in wrong. 258.847. 258.847. Okay. So this is kind of the same one, but it's an x-axis. That was x-axis as well, so that shouldn't be too bad. This one is annoying, number 12, and this is kind of, I don't know what they were thinking. But anyways, the function given is the cube root of x plus 2. Normally, because they're rotating it about the y-axis, what I would do is convert everything into terms of y, but they're not going to let you do that because they've set up the integral in terms of x. Okay, so it takes a little bit of creative thinking to figure out what the heck is the issue and how they're going to do it. Anyways, at 1, you have 1, 2, 3 at this point. At then they want to go up to 8. 1, 2, 3, 4, 5, 6, 7, 8. You can just tell from the picture. Cube root of 8 is 2 plus 2 is 4. So it's this region that they want rotated about the y-axis. So you get a trumpet type looking shape, and they want the surface area of that thing. So here is kind of our rectangle. Normally the height of that rectangle would be given by the function y, but because they want you to put the integral in terms of x, that height is actually just going to be x. Okay? So our r of x, we're going to say is x, and then our L of x, again, we could use the equation of the curve, the y equals thing, and then just take the derivative. So we're going to need the derivative is 1/3 x to the 1/3 minus 3 negative 2/3. So the L of x thingamajig is going to be the square root of 1 plus 1/9 x to the negative 4/3. And then hopefully we'll be able to figure out that integral. Okay. So this is weird. Okay, this normally wouldn't happen. Normally you would just convert everything in the terms of y, and the integral is pretty easy in that direction. Okay. This one is a little bit more complicated because of what they're doing too. So anyways, 2 pi integral x and then square root of 1 plus 1/9 x to the negative 4/3 dx, and you're not necessarily going to be able to take this as your u sub, so the 1 plus 1/9 x to the negative 4/3, because if you did that, you would get x to the negative, like something x to the negative 7/3, which would be worse, right? So what you want to do is a little bit of fancy footwork. Let's rewrite this integral as 9x to the 4/3. So I just found a common denominator, basically, rewriting this firstly as 1 plus 1 all over 9x to the 4/3. Then I found a common denominator, so 9x to the 4/3 all over 9x to the 4/3 plus 1 all over 9x to the 4/3. And you'd end up with 9x to the 4/3 plus 1 over 9x to the 4/3 dx. And then you can simplify the denominator of the stuff inside that radical. So you'd get x all over 3x to the 2/3, and then times the square root of 9x to the 4/3 plus 1, right? Because this thing right here is basically just, you could make it the square root of 9x to the 4/3 plus 1 all over the square root of 9x to the 4/3, and then the square root of 9x to the 4/3 is 3x to the 2/3, which is what I factored out in front. So that would leave you with 2 pi times the integral of, well, let's factor out the 3, and then you get x to the 1/3 square root of 9x to the 4/3 plus 1 dx, and then it should be easy. So u is 9x to the 4/3 plus 1, du will be 9 times 4/3 x to the 1/3 dx. In other words, du is 12 x to the 1/3 dx, Please don't write 72. Dividing for dx, I get du all over 12x to the 1/3. So I'll have 2 pi all over 3 times the integral of x to the 1/3. X to the 1/3 times u to the 1/2 times dx, which is now du all over 12x to the 1/3. The x to the 1/3s cancel, factor out the 12, so you get pi over 18, and then I integrate u to the 1/2, so that would be u to the 3/2 times 2/3. 2 over 18 is the same as 1 over 9, so pi over 27, back subbing 9x to the 4/3 plus 1 to the 3/2, and I'm evaluating from 1 to 8 on the x-axis. So that'll be pi over 27 times 9 times x, 8 to the 4/3. 8 to the 1/3 is 2, then 2 to the 4th, 2 times 4, 16. That's 1 to the 3/2, and then minus 9 plus 1 to the 3/2, and then that would be pi over 27 times 9 to the 3/2 is 27. Then you have 17 to the 3/2 in here, minus 8, or rather 10 to the 3/2, I guess. Ugh. Hopefully this will be right. I have my doubts. 27 times 17 to the 3/2. Times 7 to the 3/2. 216.524. That problem is just nasty. There's no reason for that. 216.524. I feel like it shaved a couple minutes off my life. Let's see what's wrong. All right, let me pause. See what I did wrong. Oh, I think I see it. It's right here. So that would change this chunk into whatever the heck that thing is. It's 9 times 16 plus 1. 145. See if that does it. If not, I'll try again. Oops. Over here. $99.480. Yeah. All right, so that one's nasty. Hopefully the other ones aren't, but you see what you're up against, hopefully, and if you need to, you can improvise, which I hope you all can do at this point. So thinking outside the box, that sort of thing. Okay, thank you for watching, and we'll see you next time.